we're going to try to be a little bit clearer this time on the topic, two completely different topics. So the first one is extended phase graphs, which is, it's like a visualization method for trying to understand the signal when you've got a lot of RF pulses. Because, you know, when we talk about one RF pulse or two, but, you know, if you've got like, you know, 100 or, which is not uncommon, you know, trying to sort of diagram what's happening in a way that your visual system can understand. That's really what this is about. And last year I was looking over the lecture last year. When I got to the end of the lecture, I said something like, "Well, I don't know. It seems this was supposed to be sort of more easy way to understand it, but I somehow made it harder." So the goal this time is to try to actually make it easier. So what's the problem? So the problem is that when you actually think of what's going on in MRI, in a case where you've got some, say, B0 defect that's causing things to get out of phase, so like slight variation in the Z component, that basically means you need zillions of copies of the Bloch equation, zillions of copies of the Bloch equation, because each one is going to be precessing at a different, in a different B field, and so that's a different block. And so to simulate what's going on as spins get out of phase with each other, each different out of phase spin due to a problem with the B0 is going to need another Bloch equation. And what is an echo? An echo is when all those Bloch equations come back into alignment. But you can see that, you know, doing that it's kind of like, it's tedious, and you end up with like, you know, I mean, when people do simulations, they'll make like 1,000 copies of the Bloch equation and then see what's going on, and it's kind of difficult to sort of visualize it all in one place. And so that's what the extended phase graphs are basically trying to do, to sort of make this spread in the phase back into some simple 2D diagram that we can sort of understand as a primate looking out at the world of this simple 2D graph. So that's the so we need, you know, a visualization method. So extended, you know, phase graph visualization method. And you can also do calculations with it if you're trying to calculate how big of an echo are you going to get. So it's possible to sort of use it in a quantitative way as well. We won't go over all the equations for the quantitative method, just sort of get the idea out there, because people use this when they're trying to design a new pulse sequence. So to start with, so the starting point is, starting point is that the an RF pulse, makes new transverse. So MT. So it makes. So if you do an RF pulse, you'll make new transverse. But the problem is, you're typically, if you're doing more than one RF pulse, well, then there's a whole bunch of magnetization already there. And so there's two, and so when we talked last, or a couple times ago, about stimulated echo, we had this idea that an alpha pulse, if it's not exactly 180, rotates a portion of existing MT into ML. And so, and flips, MT to rephase. So there's two things going on. So you flip some of the spins, and some get, the ones that were ahead get behind, and then after the same amount of time you'll get an echo. But at the same time, it also saves some of the transverse magnetization in the longitudinal, and the longitudinal is not subject to the dephasing because it's in the z direction. And so you can sort of save some of the transverse in the longitudinal. And then the second thing is that a third pulse can uncover, can flip ML back to MT and then cause rephasing and an echo. So you quickly see that you can have lots of lobes and fishes and all different kinds of pathways of recovering and non-recovering if you've got a bunch of pulses in a row. So the plan is to try to sort of diagram this in a simple way without making zillions of copies of the Bloch equation, and just make essentially one line that indicates the dephasing. So it's a phase graph. So it's basically a graph of essentially how out of phase is everybody getting. That's what the axis, the y-axis of the graph, and the x-axis is time. So it's just 2D. So the x-axis is time, and then the y-axis is pretty much how much dephasing has occurred. And you could dephase in both the negative and the positive direction, but we're going to just sort of concentrate on the dephasing in the positive direction, and when we flip, we'll have the effect of sort of flipping us down into the negative direction, and then we'll continue to dephase. But that means we're rephasing. So, okay, so there was two rules for what to do when an RF pulse occurs. And so the first rule is, transverse case. Transverse case. So we've got some transverse magnetization that's dephasing. So here's our graph of phase. So this is 0 phase, and then so this is phase going up here, and this is like, negative phase going this way. So if we've got some transverse magnetization in our system, we draw a line to indicate that guy is just slowly getting out of phase more and more because of a gradient or because of B0. So over time, so this is time, over time what happens is you just get more and more spread in the phase. And so now we apply an RF. So here's we apply an RF. And what we want to do is sort of graph out what we just sort of said in words there. So when we apply an RF, we generate 4 different pathways of phase. And so what are those 4 different pathways? One pathway is we leave some of the we're not doing necessarily a 180 or 90 degree flip, so it's some random 30 degree flip. And so we're going to leave some of the transverse magnetization continuing to dephase, and then we'll put dashes for some transverse magnetization, magnetization that we turned into longitudinal, which no longer is affected by the B0 field. So it no longer phases, or it doesn't change its phase. That's the saved magnetization. And then we also go down and flip some of the transverse magnetization so that that will begin to rephase. So this is our diagrammatic picture of how we made the ones that were ahead behind. And so after the same amount of time, this is where you get, this is where the echo appears. The echo appears right here when you cross 0. But then we also flip some magnetization into this saved pathway that has a negative phase. So it has a certain amount of dephasing, but it doesn't, once you turn it and save it in longitudinal, it doesn't get any more dephased. So when you hit some transverse magnetization with an RF pulse, you get 4 pathways that come out of it. So that's the, and we can even say like how much each path. Boy, that's kind of small, isn't it? Okay, so we can say, if we do some sines and cosines, we can say if this is the phase angle, we can say how much of how strong is the pathway, depending on what the flip angle is, because the flip angle, if you change the flip angle, it will vary how much you distribute this branch to the 4 different branches. And so this guy is 1/2 sine, and this guy is sine squared of the flip angle over 2. This guy is 1/2 sine. So this can be a quantitative thing. You can. It's not just a diagram. You can use it sort of for a quantitative estimate of how big is an echo going to be. Okay, so that's the first transverse case. So whenever we do an RF pulse, we basically get 4 additional phasing or not dephasing or just saved pathways. And then we have the longitudinal case. So the longitudinal case is the same kind of graph, except that our longitudinal magnetization is coming in at some amount of dephasing, but not changing. And when we apply an RF to that guy, we can. It's different than this starting point. So the starting point was there's no transverse, and we just generate some transverse with the RF pulse. But this is talking about if we've got some dephased, saved longitudinal. And so in that case, what's going to happen is we'll turn some of that into transverse, which will then start to dephase. And then we will leave some of it. There's actually 2 pathways on top of each other here that are 180 degrees out of phase, but we'll just leave that. And so the amount, this is just those 2 together is just the cosine of the angle. This is just the sine of the angle, like we normally do when we're just drawing our diagrams like this, and we sort of calculate how much transverse do we get, how much longitudinal is left. Okay, so that's the second one. And again, what this axis is how much dispersion, like how much positive dispersion or how much negative spread in the phase. Okay, so that's our 2 rules. And so now that we've got those rules, we can apply them to that 3 echo case that we talked about, 3 RF pulse case that we talked about. So as the simplest case, if you do 1 RF and then another RF, the same amount of time after it, you get a spin echo. And if you don't do any more RF, nothing happens. But if you do 1 RF, a second RF, and then a third RF, then you get this case where you can sort of save some of the magnetization and you can get a series of echoes. You'll get additional spin echoes after that, but you'll also get the stimulated echoes. So that's what we're just going to re-diagram that 3 echo diagram, but just to look at all the different phase pathways or sort of phase dispersion pathways using these rules. And I'll update the notes with some better annotations so you can sort of make heads or tails of the diagram, because after these phase pathways start to build up, you could have hundreds of them sort of piled up. Okay, so we start off with the, let's make sure I go far enough to the left here. Last year I managed to go off the right side of the board, but now I'm starting further left. Okay, nice and far left. Okay, so here's our first alpha pulse. And so this guy is, put 2 here and 3 here. So we got three different kinds of things. So so this year we'll put a little square around where we made some new transverse, and a circle around where we are splitting some transverse into 4, and a triangle around where we're splitting some longitudinal into 2. So okay, so here's our first RF pulse. We've waited a long time. There's nothing going on, nobody home. And so let's put our 0 on the phase diagram here. That's all good. So the first thing that happens is we get some, I want about, it's about here. So here's our second RF pulse. So the very first thing that happens is that we create a new transverse that starts dephasing from the RF pulse. So that guy starts going up like that. And that's all that happens. So this is, alpha 1 new. And so that guy is a square. So that's we just sort of started generating some. We generated some transverse magnetization that starts to dephase. So now we hit it with an RF pulse, and so that allows us to apply rule 2. So that's a circle. So at that point, we will generate 4 pathways that will come out of here. So there's going to be some saved, longitudinal coming out that way, and then it's going to flip it and cause some saved longitudinal with 180 degrees out of phase, and it's going to leave some of the transverse dephasing like this, and as you get further and further, you just get phase wraps around. So what happens is, initially everybody's lined up by the RF pulse, and then as the phase gets worse and worse, it gets, say, spread around the circle, and then it gets spread around the circle twice, and then 3 times. It just keeps going, and so that's what this line represents. It means like we're just getting worse and worse and more dephased. as soon as you spread all the way around the circle, everything is already lost. But you can continue respreading around the circle and just getting worse and worse. Well, all is not lost. You could spread around the circle like 10 times, and if you did an RF pulse, you could then be, 10 cycles ahead, and now you're 10 cycles behind, and you'll get an echo. Okay, so, and then we also cause some additional, which is the one we're really interested in, which is the one that causes the echo. So we cause some additional transverse magnetization to be flipped by 180 degrees so that it can rephase. So this is our echo pathway. And then when we reach that point, then we get our echo. So that's our first. So there's an FID here. There's the FID, and here's our first echo. So that's spin echo 1, 2. But you can see there's other parts of the transverse magnetization that have been spread. Some of it's been saved down here. Some of it's been saved over here. Some of it didn't get flipped, and it just gets even worse. And here's the only one that we're interested in, which actually causes the echo. And so when we get an echo, when we cross 0. And if we didn't do anything else at this point, everything would just continue. There'd be no more echoes. This guy would just continue to get dephased. This guy continue to get dephased. This would just continue to be saved, and it would just die. There'd be no signal come out. So the mess that occurs is when we do another RF pulse. And so when we do another RF pulse, let's put that other RF pulse right here. You can see that we could put that other RF pulse exactly at the same space as this one, right on top of here, and then we would have sort of multiple pathways sitting on top of each other, which commonly occurs and is actually desirable to actually sort of pile the echoes on top of each other. But here's our third one. Sorry, there's one pathway that I left out. So let me go back to number 2. So go back to number 2. We also created with this one. We created some new transverse magnetization that started to get dephased. So that's a case here of, that's a square case. That's like number 1 case. So this is, alpha 2 nu. Okay, but that one, that one is basically just going to sort of go off into the sunset and not do anything. So now we do the third pulse, and so the third pulse will create some new magnetization of its own. So there's going to be yet another one coming up here, like that, and that's a case of creating some new transverse. This guy is alpha 3 nu. But then it's going to hit all these other pathways. So we've got to do the circle operation. So we've got to do the circle operation on this guy, on this guy, on this guy, on this. Is that the right number of them? Oh no, sorry. We got to do the circle operation on these 2 guys, and this guy's going to be the triangle operation. Right, and this guy down here is the triangle operation. Yeah, that's what was kind of unclear. So this one is, the RF pulse is hitting some saved, and here's another save that the RF pulse is hitting there. Okay, so let's just start with the top one. So what is that top one going to do? It's going to make a pathway down here. So it's going to make some saved longitudinal here, and it's going to make a 180-degree rotated one, which just barely makes it to the echo. And so that one is going to make a little small echo over here, and that guy is going to be spin echo, which was that one from? That one is from this one. Spin echo 1 and 3. That's the furthest one out. Yes. Okay. So, and then it's also going to save some transverse in the longitudinal here, and it's also going to add on to this guy. Okay, so there'll be like 2 lines on top of each other there. So that was applying rule number 2 to this guy. Okay, now we got to apply rule number 2 to this guy, and so the same thing happens here. So we've got save some transverse and longitudinal there, add on to this guy, and then go, where's 0? 0 is here. This distance down, and save some inverted phase, longitudinal, and then also do some rephasing, and that guy will make another echo. So this guy is the combination of pulse 2 and then pulse 3. So this is spin echo 2, 3. Okay, so I did that guy, and then there's one more guy here. So what is this one? So this one is, it makes some saved longitudinal there, and then it makes some saved longitudinal here, and it makes some rephasing, and that guy makes the secondary echo. So there's another echo there. That one's called the secondary echo. That one was the one that was, it kind of treated this echo as if it was an FID, and then it rephased it. So that was the secondary echo. That one continues up into oblivion. And what did we forget? We forgot to put in the FIDs. So here's the, don't want to mess this guy up too much. Here's the FID from this guy. Okay, and then last but not least, we have the stimulated echo. And so how does the stimulated echo actually work? There's 2 pathways for the stimulated echo. So those are the triangles for the stimulated echo. So what happens at the triangle is that we get some saved, just continuous a portion of the magnetization as saved transverse that was sort of saved into the longitudinal, but then we turn some of it into transverse. And this guy just goes off into oblivion. It's not going to make an echo. And so that one just sort of goes away. But this one down here is the one that we're interested in, that makes the stimulated echo. And we're particularly interested in that because the decay of this signal is much slower because it's saved. It's still decaying, but it's decaying with a T1 constant instead of a T2 constant. And so that one is the one we're interested in, and that one comes out here like this. And that one crosses and makes this really big echo. So this echo is the stimulated echo, and that one's really big. But now let's look at like what caused it. It's like what pathway caused it. I'll just draw it in a different color. So that one required all 3 pulses. And so there's 2 different pathways that caused it. So one of them is like this, goes like this, and then it goes down, and then it gets saved, and then it comes back up again. So that was one pathway that generated that echo that involved all 3 pulses. And then the other pathway goes like this. It continues across over here, and then it gets flipped down here, and then it goes up. So you could either dephase, flip 180, get saved, and then rephase, or you could dephase, get saved without flipping 180, then flip 180, then rephase. And so these were the 2 stimulated echo pathways. Now, normally nobody in their right mind would draw this out like I have here. You would just use a computer program to do it. And certainly if you ended up with 100 RF pulses, you would definitely use a computer program to do this. But believe it or not, it would be simpler than simulating 1,000 Bloch equations. And each time you end up with another pulse, you're going to sort of multiply the number of Bloch equations that you have to simulate. And so I think I did a better job this year of giving you an idea like this could actually be a useful thing. This was thought up a long time ago, 50, 60 years ago, in the days before fMRI. It was just thought up by chemists doing spectroscopy. And so this is the extended phase graphs. Extended phase graphs, visualization method for trying to sort of see what happens when you do lots of RF pulses, and there's a whole bunch of different magnetization floating around there. Okay. So any questions about this? Extended, yeah.
The secondary echo, is that originating from one of our rules that we applied to it?
Yeah, it is. So the secondary echo is, so this guy's the secondary echo, and so at this point, where's the secondary echo? No, at this point here, it comes, it's completely clear. It comes from this guy. Yeah. So what was happening here is that this was the spin echo 1, 2, and that guy, this part of spin echo 1, 2 sort of acts like as if it was an FID, and so that's some dephasing transverse magnetization that's heading up here, and we hit it with RF pulse 3, and so then it makes it leaves some dephasing, makes some saved longitudinal, flips 180 degrees, makes some dephasing, dephasing down, rephasing down here, which is the one that makes the echo, and puts some 180 degree out of phase saved longitudinal there. Yeah, so that one came from this transverse case rule. Yeah, and like I said, you would normally do this with software to make the graphs, and so that but you could end up, you're basically, what do you what's the point? You've got this complicated thing with 3D vectors moving all around, and then you got thousands of copies of them. You're just trying to reduce it. What's the goal? Reduce it to a 2-dimensional graph that a human can look at like a picture. That's really what the goal of this is. It's kind of to sort of make a graphical picture of these thousands of equations. Okay, so I was definitely better than last year. So that's a keeper. So any other questions about the extended phase graphs? So you can go online and look at the software for doing this, or look at papers. It's not like the MRI physicists completely understand it themselves. If you read some of the papers, you can see that they're just using it as kind of like a visualization tool. A lot of them not fully understanding it, sort of like me or you. Okay. So we'll start erasing unless there's any other questions about this. Yeah, I mean, one very commonly used pulse sequence is called a fast spin echo pulse sequence. And this fast spin echo will often have something like 150 or it'll have a 90 followed by 150 RF pulses. And so they're generating, each pulse is splitting the pathways. And so you're ending up with like millions of pathways on top of each other. And those pulse sequences are partly designed using something like this to sort of see how we can sort of pile the echoes on top of each other or stop the echoes from interfering with each other. And there's one other thing that these graphs are used for is a lot of times when you're doing all these pulses, you end up with some excess magnetization that you don't want. And so then you do another RF pulse called a crusher, which is intended to sort of damage the magnetization. But of course, whenever you do another RF pulse, you're going to generate these four pathways again. And so that's another kind of a pulse. Like, we did some pulses and we've got some magnetization, but we want to get rid of it now because we're going to start again really quickly. And so if you're trying to design a pulse like that in order to sort of clean up the room before you start another data acquisition, you have to sort of consider all the pathways that it's creating. And so that's another thing that these graphs are used to design. Okay, so now complete change of topic to something that's kind of like inversion recovery. So I haven't talked about the whole sequence, the full pulse sequence of how this is done, but we'll just talk about the preparation part. Because sometimes when you talk about inversion recovery, you think of it as a preparation before you went and did the pulse that's going to generate the magnetization that actually generates your signal. So the inversion pulse is often called a preparation pulse. And so what is the basic inversion recovery sequence? It was, we start with a 180 and then wait a while and then do a 90. And that was and then make image. So here's when you make the image. So that's why it's a preparation pulse. And so that amount of time was the inversion time. And what was one of the goals of doing this? It was to basically try to zero out one kind of tissue. So if you draw the longitudinal magnetization that's going on here, what does it look like? Hopefully we would have waited for a really long time. We're going to remove this long time in the next diagram. So wait for a long time so that basically all the different tissue types are all the same. Because they all finished their T1 regrowth, and so there's no difference between them. Because if there was a difference between them, we would end up with a difference down here. So say like, say this is, like gray matter and white matter, and they're both on top of each other. I'll draw it in a different color. So here's gray matter and white matter. So this guy is, say, white matter, and this guy is, gray matter. Let's just assume that they have the same T2 value and the same proton density. Don't exactly, but that's close enough, because that guy's a proton that tells you the proton density. Okay, so if you do a 180 pulse, you'll flip, and remember this is the magnetization longitudinal, so the one you can't see, you'll flip both of them down to the same point, so they'll both follow each other down there, and then they'll start to recover, but the white matter will recover quicker. So here's the white matter. This guy will recover a little quicker because its T1 number is shorter, and so that means a quicker recovery. And so that guy's the white matter. I'll just color it in. And so then the gray matter is recovering slower. I'm exaggerating what the difference is, but gray matter is recovering slower. And so if you can arrange essentially to have enough time so that the gray matter reaches 0 and the white matter has some longitudinal magnetization. Remember, this is longitudinal, so it's just the Z. Then if you do a flip at this point, a 90-degree flip, so this was the 180 here, and if you do a 90, what will happen is you should get really good contrast between those tissue types, because you should get no signal. There's no longitudinal magnetization for the gray matter, and there's a small amount, but something that's a lot bigger than 0. So here's the white matter and gray matter. So this is a classic way of trying to make a lot of contrast between two tissue types. And then you have to make image. You have to make. I didn't describe how to do that, but you got to do a bunch more pulses to make the image. So what's the MDEFT idea? So the MDEFT idea is, why don't we just add another 90 before the 180 before the 90? So the MDEFT idea is put another 90 in here. Why would you want to put another 90 in here? So basically this is in version recovery, and then all these three, and then you still have to make the image. All these three are MDEFT, what it means. It means something like, that means Fourier transform, but magnetization, something, Fourier transform. Unfortunately, we have all these acronyms, but they just become words, and the meaning of MDEFT is 2 preparation pulses before you do the 90 that is the one that you make the image from. And so what's the point there? So the point there is that we have a situation where, so let's just draw out like something like this, what's going on. So here, here's a copy of that. So we've got some magnetization to start with. We do a 90, and then we get some recovery, and there might be some difference between it. Sorry, before I start that one, let's say what the problem that can occur with this one is, and then that will sort of like make a reason for doing the MDEFT. Okay, so this was kind of the idealized situation, but what if we happen to start up another pulse before all the difference between the gray and the white matter went away, because we're trying to collect data faster, and we're always trying to collect data faster. So in this case, what happens is, say this is what happens to the gray matter, but say the white matter has recovered a little quicker. And so the white matter is up here. What's going to happen then is that this guy is going to, I'm exaggerating, but this guy is going to give you a bigger signal. And then what's going to happen is, you can see this guy is going to cross that guy. And that's going to kind of screw up our plan of trying to have a big difference when one of them was crossing 0. And so this guy would be the white matter recovering more quickly because it's got a shorter T1. But this was also the white matter that recovered more quickly because it's got a shorter T1, because we didn't wait long enough. And how long do you have to wait? You have to wait like 5 seconds or something like that, a really long time to get rid of that difference. And that's ages when you're trying to collect data quickly. So why would we want to do the MDEFT? So the MDEFT would be to sort of stamp out some of the difference between this. And so the way this would work is, if this is 0 here, so we start off with a difference. So we start off with a difference, but instead of doing 180, just do a 90. And so here's our difference. And so when we do a 90, we kind of stamp out the difference, because we're starting them both at 0 now. And so then what will happen is the gray matter will start recovering, not quite as quick, and the white matter will recover a little quicker. And then when we do our flip, we'll have less of a difference than we would in this case. So now we'll still have a difference, so this guy's still going to go down further, but there'll be less of a difference. And so we'll have a better chance of basically allowing this guy to, recover faster. Sorry, I didn't do that right. Allowing this guy to recover faster so that we can basically get a big difference when we're crossing 0. Okay, so this guy is going to go like that. And this guy's going to start a little bit lower, but pretty quickly get ahead so that we can end up with a pretty big difference there. So when you look at this, there's all these little small differences, but that's all that matters, because if you don't have any difference between the tissue types, then the gray matter and the white matter look exactly the same, and the image is like completely useless if you're trying to distinguish gray and white matter. So this is kind of assuming some stuff that we haven't talked about yet about how you actually make the images, but just gives you some idea. So this is like a double. So this is, idealized, actual, if not fully recovered, and then, MDEFT fixed. Which is basically double preparation. And you could run Bloch equations and end up with like an expression for what you would expect the brightness of a voxel to be given a given T1, a given time for the 90, given a time for the 180. So this is this is our first 90, and then we do a 180, and then another 90 here, and then, you know, make image. Here. So that's not drawing out the whole sequence, but you could end up with an equation, and then from that equation for the brightness of the MDEFT signals, then you could determine what the optimal setting of the spacing between the 90 and the 180 and the 180 and the 90 would be. And the thing about this is again, you can adjust these things. If you have an MDEFT sequence on the scanner, you can adjust all these numbers, but you know, if you don't have some feeling for what they're doing, it's just like you're just totally guessing. You're just sort of experimenting around, just trying it. And so once you've collapsed this to a single equation, then you could easily see what, you know, would be for a given T1 value, what would be the optimal timing for these various things. Okay, so I think that one was also a little clearer than you asked last year. So any questions about sort of two preparation pulses instead of just one? Both of these kinds of things are commonly used, especially inversion recovery or something like inversion recovery. We'll talk about MP rage. It's the most commonly used structural sequence for looking at T1, gray matter and white matter. So any questions? All good? Yeah. So the problem is if we don't wait long enough, then what happens is we're going to start off with a difference between them as they recover, and then given the sort of general scale of these curves, what's going to happen is when we get to when they're crossing zero, when one of them is crossing zero, the other one is going to be sort of crossing zero because this white matter is recovering faster. And so if it's recovering, so what we're trying to do here is the white matter is recovering faster, and so we wait until the gray matter hits zero. And the problem here is the white matter is still recovering faster, but because they hadn't fully recovered from the previous mess, you're going to start off with a signal for the white matter that's more negative. And so then as it recovers faster, it blots out the difference that we would hope to get when they pass zero. Yeah. Okay, Stan, I think we'll end the recording there.